In this video, we're going to introduce significance tests for means. So we just did significance tests for proportions, and now we're going to do the same procedure for means, just like we did with panic and the one proportion z interval, and then we switched to the one sample t interval. For means, we're going to do a one sample t test. So just keep in mind we're looking for the keyword mean or average. So this was an example earlier in the chapter. It said a company has developed a new deluxe AAA battery and it's supposed to last longer than the regular battery. But these are new, more expensive batteries, so they want to be convinced that they really do last longer. Based on the past, the old batteries lasted for 30 hours. So we're going to underline that. And that seems like that's the old mean on average. So notice this is a mean question, so we want to write the word means. And we're going to write down mu equals 30 based on the past, the length of the hours of the battery. Now they do a simple random sample, which is n of 15 batteries, and they use them and they see what is the battery length of these 15 from the sample. And they want to see if this is enough evidence at the 5% level that indeed these new batteries last longer. So notice here in this example, we have a list of data. They did not give us the sample mean, which is x bar. We don't know it. And we don't know the sample standard deviation s. So we're going to have to put this data in L1 and run one variable stat on the data, okay? So do this, you have to press stat 1 edit, enter the data in L1, and then once it's entered, you want to press stat, go over to calc, and you're going to choose number 1, 1var stats, and make sure that it says L1 and nothing's in your frequency list. So please do this now. I actually already did this in my calculator. I pressed stat edit, and I have all my data here in L1, and now I'm going to run the 1var stat for you. So I'm going to press stat, calc, 1var stat, L1. Make sure this frequency list is clear and hit calculate. So we're going to get our sample mean, which is called x bar, which is 33.9333. And we're also going to get our sample standard deviation, which you're going to use the one that says S sub x, not sigma. So 9.816 hours, okay? So on average, it looks like the sample lasted for 33.93 hours. And on average, these values length deviated from the mean by 9.816 hours. Okay, so this is our sample data. Those are called statistics because they come from the sample. All right, and it's a mean question. So remember, for a mean question, we would often use t. If we don't have sigma, we're going to use s in place of sigma. So this is going to be some kind of t procedure. All right, let's keep that in mind going forward. All right, so it says state the population of interest and the parameter of interest. So where do they take the batteries from? It seems like they took them from the deluxe batteries, AAA batteries. So the population is all new deluxe AAA batteries of the new variety. And now the parameter. So the parameter is going to change here. Remember, we just came off of the proportions. Now we're going to do mean. So we're going to use the word mean, and we're going to use the symbol mu. So this is the true mean battery length of the new batteries. All right, now let's do our hypotheses. The null hypothesis and the alternative. The null is the statement of no change based on the past. Remember, it's always an equal to sign. Remember, we always use the parameter. So instead of p, we're going to use mu because it's a mean question. So the mean from the past was 30 hours. So the null is going to say that the mean is still 30. And in words, that means these new batteries have the same battery life as the past. The old batteries, basically. Okay. And then the other one is going to be that they last longer. So that's going to be HA greater than sign. That's a one-sided tail. And that's the new batteries last longer than the old batteries, the standard ones. All right. So hopefully you're feeling confident that we're really just doing the same thing here with phantoms. Population of interest, parameter of interest, hypotheses. The difference is just that we're using the symbol mu here instead of the symbol p. So just shift gears. So now it says check if the conditions for inference are met. So what are the conditions for mean? So we did this back for interval, for one sample t interval. Let's remind ourselves what they are. So if you look down below, it says random, so is it an SRS? The 10% rule, and is n large. Remember, for proportions, we did NP and NQ greater than or equal to 10. For this one, we want to know either is the parent population normal or is the sample size large enough to use the central limit theorem greater than 30. If not, then you have to plot the data and you have to check for normality. If there's any strong skewness or outliers, you do not proceed, okay? So this is all review from our one sample t interval, okay? So let's go through these now. Number one, is it an SRS of 15 batteries? If you go back to the top, it said it was. Great. Next one, 10n. 10 times n equals 10 times 15, which equals 150. Is that less than the population of all new AAA batteries? I'm sure it is. And the last one, is the sample size large enough? Since n equals 15 is not greater than 30, we can't use the central limit theorem. So we don't know that the overall population is normally distributed as well. So what we have to do is plot the data. So this is when they give us data, we put it in the list and we plot it. Okay, so there's a couple of ways we can do this. We press second y equals, hit enter on plot 1, hit enter on the word on. Remember, my data is already in L1. And then I'm going to go down and I'm going to choose this type, which is called the modified box plot, or you could choose the last one, which is the normal probability plot. I'm going to show you both. So if we use our modified box plot, we make sure nothing's in y equals, and then we're going to press zoom 9, which is zoom stat. So if you choose zoom 9, the box plot should show up, and if there's no outliers, then there will be no separated marks separated from the whisker. So it looks pretty good. So we can plot our data and refer to the plot. So let's do a quick sketch of what we see. It doesn't look too bad. The middle 50% looks approximately like slightly skewed left. Now slightly skewed right, sorry, because it's a little longer on the right within the box, but then the whisker looks a little longer on the left. That's what I meant. Okay, so I'm going to say this is approximately normal with no extreme outliers, extreme skewness, and no outliers because it didn't show anything separated from the whiskers. The other thing that you could do is go to the normal probability plot, which you press second y equals, plot 1 on, go to the last one all the way on the right, and you just hit graph or zoom 9 again. And you're going to see that this looks pretty linear. The more linear it is, the more approximately normal it is, the more the data is not skewed. So it looks pretty good, okay? So now we are done with our assumptions, and we're going to be ready to proceed. So what are we going to proceed with, right? So we have to think about where we came from. So hopefully you guys remember that when we were doing our phantoms for the z-test, we would do the test statistic with a z-score. And basically now, because we don't have sigma, which is right here in the reference sheet, we have to replace sigma with s. And as soon as we do that, then there's some error present. So that's why it's going to be called standard error. So when we do statistic minus parameter over standard deviation of the statistic, it becomes standard error. Remember, the standard deviation of the mean is going to be sigma x bar equals sigma over radical n, but now since we're replacing sigma with s, it becomes s over radical n. So this is called standard error of the mean now. So we end up doing a t-score or a t-test statistic instead of a z-score. And the degrees of freedom, remember, is n minus 1. So just a quick reminder that the t distribution is quite symmetric like the z, but it is not normal because it's more spread out. The spread is greater. So it's still symmetric. It still has a single peak and a bell shape, but it is more spread out, which means more variability than the Z distribution. And remember, to get the degrees of freedom, you do n minus 1. Remember, as the degrees of freedom increase and the sample size increases, it becomes more normally distributed. Approximately normal, I should say, okay? So going back to our battery question, if we go through phantons, we did P, we did H, we did A, we're going to go to the name. The name of the test is going to be called a one sample t-test. Okay, so no more proportions, and it's t instead of z. And now we're going to do the test statistics. So we just showed on the last page, it is a t-score, and it is statistic minus parameter over standard error of the statistic. The statistic is going to be the x bar. The mean is going to be mu x bar, which equals mu, and the standard error of the statistic is going to be sigma x bar. It's going to change to S over radical n. So we still draw our bell curve. In the middle, we put the mean that we're assuming to be true in the null, which was 30, and then we're going to shade in the direction of our HA. So we got an X bar. If you look in part A here, we got 33.9333. 33.9333 is to the right of the mean. So you want to put a line to the right, label it 33.9333, and we want to shade to the right because that's the direction of our HA. So we're looking for the probability that X bar is greater than or equal to 33.333, meaning how extreme, what is the probability or the likelihood of getting a value as extreme or more extreme than our sample result just by chance. So when we plug in our numbers into our t-score, we're going to get X bar, which is 33.9333, minus the mean that we're assuming in the null, which is 30, over, now remember, it used to be sigma over radical n, but because we don't have sigma, it's going to be S. So once we do that, it's going to be called standard error of the mean. So we're going to plug in our S and our radical n. So our S from our number 1 was 9.816, and our n was 15. 9.816, square root of n, square root of 15. Now we're just going to go to our calculator and we'll be done. So we're going to go over to stat, go over to test, and we want to choose number 2, the t-test. Choose it. And now data or stats. Well, guess what? We have data in our list, so that's exciting. So we can just put our null hypothesis, which was 30. It's going to calculate the mean for us from L1, and you just pick a greater than sign because it is the HA, and you could choose calculate or draw. If I choose calculate, I'm going to get my t-score, which is 1.552. I'm going to also get my p-value, obtain my p-value, and my p-value is the second line here, 0.071. And then I can make my decision. Now I do also want to show you that if you scroll down here, it gives you X bar and S, and it gives you N, okay? All right, so let's make our decision. Based on the alpha equals 0.05 level, do we reject the null hypothesis? I'm hoping you're saying no, because p is a little too high. So we want to say, because my p-value of blank 0.071, whoa, is not less than alpha equals 0.05. It is not statistically significant at the alpha equals 0.05 level. It is not statistically significant at this level. Thus, I can't reject HO. You could also say I fail to reject HO. Thus, I can't conclude that the true mean number, thank you, of length of the battery life of the new batteries last longer than the current batteries, which is 30 hours. So basically, I can't conclude that they're significantly doing longer and better, and thus I cannot make a distinction that these batteries are worth the money. So that's the story.